Hello and welcome to lesson 7.7 on partial fraction decomposition. This is the final lesson in Unit 7 and probably one of my favorites, although I really like lesson 7.2. That might be my favorite one. I don't know. But this one's really great too. And so what it's about is, in lesson 7.4, we talked about adding fractions. There's an example here that I'm going to just really zoom in on, right? Suppose you wanted to add these two fractions. Well, in order to add fractions, you need a common denominator, right? And so to do this, you would say, oh, well, you have a factor of x minus 1 and a factor of x plus 4. So you need to multiply by x minus 1 on top and bottom here. And you need to multiply by x plus 4 on top and bottom here. That way they have the same denominator, x plus 4 and x minus 1, right? And so that works given here. You have this. It leads to this line, at which point you distribute and get this. And then once you have that, you combine your like terms, and you're left with our final rational expression, 3x plus 7 over x minus 1, x plus 4. Yeah? And that's what we talked about in 7.4, is just combining fractions together to get a single function, a single ratio, right? And that was it. Well, what we're doing today is saying, if I gave you this fraction, could you, the word being decompose, could you decompose, which is in other words to say break up this fraction such that it's the sum of two smaller fractions, right? When I say smaller, I really am referring to of smaller degree and simpler terms, yeah? Here's an example. I'm going to do 7 over 27, right? You see, or actually, how about 7 over 9, right? If you wanted to break up 7 over 9, well, there's multiple ways you could do that. But you could say that it's 6/9 plus 1/9. And then 6/9 is actually a simplified fraction 2/3. So one decomposition of 7/9 is to break it up into 2/3 added with 1/9. Is this the only way? No, but that's because these are, numbers and not variable expression, functions. The thing is this sum, or I should say, this polynomial, this rational expression, can only really be broken up as these two fractions. Yeah, that's really the only way you can do it. I suppose you could change the denominator and numerator a little bit, but really, it's at its core, it's going to be decomposed into two main fractions, okay? So, there's a warm-up here, and if you're trying this for the first time, you haven't watched it in class, done this in class, what I would recommend is try separating this fraction right here. Try separating 4x plus 7. I don't need to rewrite it. It's right there. Separate this into a denominator x plus 3 and x minus 2. Okay? And just think about it. You don't really know any techniques or strategies. You just kind of play with it and guess around until it makes sense, until you get it. Yeah? So if you want to pause the video and give that a go, try that out. And if you want to see the answer, I believe the answer is 3 here and 1 here. Yeah? And if you're saying, how did he do that? Well, I'm going to show you techniques, but kind of by looking at it, you know that this top number gets multiplied by this denominator when adding them. So if you didn't know that top number, it'd be this thing times x minus 2 plus, and then it'd be this number. I don't know what that was really, so it'd be another question mark times the other denominator, x plus 3, yeah? And so this would be x plus 3. Also, this is totally unrelated, but does that kind of look like a cat to you? Okay, let me show you. That's crazy. Whoa, it's like a cat. Okay, I'm going to stop there. This is, you say, Mr. Spake, your ADHD is coming out. I'm saying, I'm sorry. Okay, so anyway, I mean, it looked like a cat, right? Okay, anyway. So the question would be, what goes in these question marks, right? And then it'd just be kind of a game of guess and check. Well, it's going to be something x minus 2 times something plus something x plus 3 times something. And those somethings aren't quite the same. And then that's where you play with the numbers a little bit until you find that this something had to be 1. It had to be 1x minus 2. And that this something was a 3. And then so it was 3x plus 3 times 3, which was 9. And then when you put those together, 3x plus x is 4x, and 9 minus 2 is 7. So that's kind of a breakdown for that. But this was just kind of done guess and check, and it was a warm-up that we talked about in class. Now that we've sort of seen that, or maybe you've explored it, we get to the techniques, okay? So what is the point of today? Well, the point is to learn an algebra technique. It's a way of splitting fractions up into simpler terms. And you might say, when is this technique going to be useful in math? And I would say, well, there's a class called BC Calc, or Calc 2, where this technique is actually very useful. It's called integration. There's certain integrals of stuff where it's really difficult to take the integral of that fraction, but if you split it up into smaller fractions, it's actually very easy to do. I can't say much more than that because we are quite a bit a ways from BC Calc right now. We're in Algebra 2. You still got to take pre-cal and all that good stuff. So anyway, you will see this again in that class, but this is just to give you the kind of foundation and really strengthen more of your algebra skills. Learning this really just gives you more power in how you think about algebra. And it also connects some really cool ideas from the past that you haven't probably thought about in a while. So, table of methods for decomposition. So we're going to be breaking up these fractions, and depending on what the denominators are, they're going to be broken up a specific way. So the first one we saw was something very simple, linear factors, okay? So if you have linear factors in the denominator, you can read that. The example being, let's say like blah, 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 over x minus 2 plus x plus 5. If they're single linear terms, you simply split the fraction where each factor is separated. So x minus 2 and then x plus 5, those are the separate denominators, and that's it. The constants a and b here are the things we don't know. Why choose a and b? Well, because they're the start of the alphabet. You might say, really? And actually, yes. Actually, you know what? Okay, I mentioned this in class sometimes, but if you haven't heard... okay, I'm sorry. I have to do a little bit of math history here. Yes? Variables used to be A, E, I, O, U. Vowels, yeah? Variables used to be vowels. This was established by Viete. I don't know where there's an apostrophe there. It's like an accent like there. Or maybe it's there. I don't know. But Viete was doing algebra and stuff, and he wanted to come up with a common system for writing variables. So he chose A, E, I, O, U. Problem is, that's 5 vowels. And eventually, you run out of vowels. And if you have multiple things you need to solve for, well, you don't really have a good naming system anymore. You could say, and sometimes why, but then what if you had 7 variables, and then, that kind of breaks apart. And then this guy, Descartes, comes along. René Descartes. I talk about him all the time in class. And he's the guy who starts doing X, Y, Z and ABC. And what he does is, and he didn't tell anyone to do this. He just came up with his own naming system for himself. He uses letters at the end of the alphabet to be variables, and he uses ABC to be constants. So letters at the beginning of the alphabet are constants. They're unknown quantities, but they don't change. They're not variable to things. And you can see that in this expression right here. I know, I'm just injecting all sorts of stuff. This isn't even part of the lesson, really. I'm just having fun. It said this is A and this is B because those numbers don't change. They're not subject to variation. Once you find them, I don't know, maybe that's a 7 and that's a 5, that's not going to change. But X is a variable. Why do X, Y, Z? Well, we often work in 3D systems, so you really just need 3 variables. And you'll find that in all these examples, every time you add more and more, A, B, C, D, and you could just keep on going, right? And then you really don't run out. And hopefully you don't have 26 variables because, well, then you need to name them a little bit different, but hopefully you're not going to have 26. So anyway, that's some context for you, some little math history there. If you ever wondered, why X? Yeah, okay. Getting back to what I was talking about, you say, Mr. Spake, you're yapping again. I said, I'm sorry. I'm having fun today, okay? I'm having fun. So that's how you separate linear factors. Now, come down here. The next one is called repeated linear factors. So what this is, it says create a partial fraction for every power of the linear factor in the denominator. So suppose you had, blah, blah, blah over x plus 1 cubed. And maybe there's some other stuff on the denominator too, but the decomposition of the x plus 1 cubed would separate into x plus 1 to the 1, x plus 2 to the 2, and x plus 1 to the 3. So they're all linear factors, right? X plus constant, that's linear because it's just degree 1. But it's called repeated because it has multiplicity 3. Remember that word? Multiplicity? Multiplicity is how many times your factor's actually occurring, especially in the denominator there, right? So it has multiplicity 3, so we count it 3 times. And you might be saying, why do I have to do that? Well, earlier I kind of was talking about like number over 27. And if you think about decomposing that, what possible fractions can add up in terms of 27ths? Well, 1/3 could, a 9th could, and a 27th obviously goes with 27ths. I'm not going to assign actual numbers to this, but what I'm saying is you could add thirds, 9ths, and 27ths to get something in terms of 27ths, right? And this is because the factor 3 is repeated 3 times, right? The factor on bottom being 3, this is 3 to the 1, 3 to the 2, 3 to the 3. That's why you do this rule, yeah? So that's the purpose and reason behind that. You can't assume that, it's just going to be, for instance, constant over x plus 1 cubed. You have to account for all possible fractions that could lead to this common denominator here, okay? Okay, the next one, irreducible quadratic factors. So what is this? Well, quadratic, that's x squared. Irreducible is another way of kind of saying not factorable. It's not really the same thing, but kind of is, yeah, in layman's terms, I suppose. So example, x squared minus 9. You know that factors as x plus 3, x minus 3, because it's a difference of squares. But if you had x squared plus 9, you can't factor that, not with real whole numbers. So, and not just whole numbers, but, rational numbers. You can't do a rational factorization of this. So we say not factorable. This is what's called an irreducible quadratic. You can't factor it into linear terms, so it can't be reduced, right, to linear terms. And so that's that word, irreducible. So if this happens, and you get a quadratic in the denominator, like this, something over that, the denominator is x squared minus 5. You don't separate it at all, but the constant on top isn't a constant, it's a linear equation. And the reason for this is when you separate, if the degree on bottom was 2 and you're trying to separate this fraction, when it's not actually dividing into it, then the degree on top is always going to be at most 1 less than the degree of the denominator. I know that sounds kind of weird, but what I mean by that is if it's quadratic on bottom, the highest degree you could have top is degree 1. Now, what that might mean is, we may solve for ax plus b and get no b. And so it's just constant times x over this. Or, even though we set it up like this, maybe there was no ax. Maybe we got 0 for a, and then it was just a constant over this. But you don't know, right? Because it could happen. And if you kind of skip down here to higher order factors, this carries for all powers greater than 2 as well. If you had a power of 4, then 1 less than 4 is a degree of 3. So you would want to do a cubic on top and on top here. Now it may be that maybe it's ax cubed and then there's no square term and there's no constant, right? And so it turns out you only get this on top, but that's just it. You don't know. You don't know what could be up there. Okay. Last, maybe not totally last here. Then there's the repeated irreducible. So if you understand repeated linear and you understand irreducible, it's just 2 and 2 together. So you can kind of see this, right? Irreducible, you do a linear on top. Irreducible but repeated means you do the factor 1 time down here, then a second time. But on both of those fractions, you have linear terms on top, okay? And then the last one, this is the rude one, improper fractions. So if it happens that the degree of the top is more than the degree of the bottom, for example, x cubed plus 2 over x squared plus 1, well, I don't know if you remember from 7a, this causes a slant asymptote kind of business, right? And if you want to break up this fraction, because the degree on top is more, you can actually divide part of this denominator into it. And if you're saying, what do you mean? Why would I do that? Think about 10/9. You could decompose this into 1 plus 1/9, right? It means 10 is higher than 9, so 9 could go into 10, getting you a whole number, and then you have that 1/9 kind of left over. Or, if you had 22/9, 9 could go in 2 times, but then you would still have, 4/9 left over? And so that's what this is referring to. If the degree on top was more, you would do polynomial long division, right? And get this plus a remainder. And the remainder you get, say it's like x over, or maybe it's like 1 over x plus 2, right? Then once you have that remainder, or maybe it's more, it'll follow one of these patterns. Yeah, so if ever the degree on top is more, you can divide it and then go back to these patterns, okay? Now, that's a lot, and you're saying, Mr. Spake, I'm feeling a little overwhelmed right now, and I said, that's okay. You're in Algebra 2. You don't need to know all of this right now. This is what's coming in BC Calculus. So, okay, what is my expectation for this unit for this test? I would like you to know linear factors, repeated linear factors, and irreducible quadratics, okay? I'm not going to throw repeated irreducible. That's a hassle. That's a lot of unknowns to solve for, and I don't need to complicate that for you. Higher order factors, you'd need more and more advanced factoring techniques. You remember the rational root theorem? We're not doing that right now. I love that theorem, but I don't want you to worry about knowing that, so we're not going to hand you that. And I'm definitely not going to hand you improper fractions. But just know that you could do this, okay? You're not limited to, but I just don't want you to, don't stress out about what's going to actually be tested on this. It's really just these 3. Understand the linear terms, the repetition of linear, and then the quadratics, okay? Okay, so let's work some example problems and see how this goes. I'm having fun in this video. Method 1, zeroing out. And I guess I should explain this. In this video, I'm going to talk about 2 methods for partial fraction decomposition. Method 1 is my favorite. It's called zeroing out. And when the compositions are really simple, or you don't have a lot of variables or constants to solve for, this is probably the quickest way to do it. Though, if the numbers get really big or if they get complicated in any way, then you might want to move to a different method called systems of equations. You might say, ooh, systems. I remember something. That was Unit 3 in this class, right? And yeah, some of that stuff from Unit 3 comes back here for our aid here, okay? Okay, so let's see method 1, zeroing out. It says, decompose the rational expression. And so I have this. The way I start these problems is by factoring. And you only need to factor the denominator. You don't need to factor the numerator. This is because the denominator is what's going to determine, again, how our fractions are set up, like in here. Okay? So, do an X puzzle. 2 times negative 3 is negative 6. This is negative 5. I'm looking at the denominator right here. Looks like 6 and 1, where 6 is negative, is going to work. And I'm going to be lazy and do kickback method as much as I criticize it. X minus 6 over 2, x plus 1 over 2. That simplifies as x minus 3, and then kick back 2x plus 1. Okay? It's a dirty factoring technique, but it is effective. I do kind of like it for that. So 3x plus 5 over 2x plus 1 and x minus 3. Okay? And that is our factored expression. So I look at the denominator. What are my types of factors? Well, 2x plus 1 is linear. X minus 3 is linear. That means I have 2 linear factors. And that's it. Just 2 linear factors. Done. Okay? And so I want to decompose it now. So I'm going to rewrite what I just did. Okay? Like so. Okay. Now, this needs to be broken up into 2 fractions. If you go back to this rule sheet, which is why I have this here, because it's just 2 linear factors, they're just constants on top. We're going to call those A and B and separate each of the factors in their own denominator. So it's going to be A over 2x plus 1 plus B over x minus 3. And it doesn't matter where A goes or B goes. It just doesn't matter. You're going to find out these numbers, and it's going to work out the same way. Now, what we have done is set up an equation. That goes back to lesson 7.6. We know how to solve equations, right? We talked about in the last lesson, how do you get rid of denominators in an expression? You multiply by the least common denominator. So what I'm going to do is I'm going to take this entire thing, and I'm going to multiply by the LCD, and the LCD being 2x plus 1 times x minus 3. Now watch what happens. This first fraction, when multiplied with this, the 2x plus 1's cancel, and the x minus 3's cancel. That means I'm left with 3x plus 5 equals. And I got to make sure I distribute this to all terms. So now, a over 2x plus 1, this denominator cancels with 2x plus 1 in the LCD that I'm multiplying by, but the x minus 3 is still there. It didn't eliminate, so it's a times x minus 3. Then, b over x minus 3, you take this, the x minus 3's will cancel each other, and you'll still have 2x plus 1. So it'll be plus b times 2x plus 1. Fantastic. Okay, and that sets it up. Now, to note, just a little star here, asterisk. For both method 1 and method 2, this setup is the same. So you set this up, okay, create the decomposition, and then multiply by the LCD to get a nice, pretty equation like this. At this point, this is where the 2 methods are going to be different. So the zeroing out method is a way of using roots of your factors to zero out unknowns, meaning get rid of them. And you say, what are you talking about? I say, look, what are the factors here? The factors are x minus 3 and 2x plus 1. What are their roots? In other words, what makes those 0? Well, 3 minus 3 is 0, and negative 1/2 times 2 plus 1 is 0. So those roots are what I'm going to plug in for x. Watch, x equals 3, right? put a little colon here. I'm going to plug in 3 for all the x's, okay? 3x plus 5. That's 3 times 3 plus 5 is a times 3 minus 3 plus b times 2 times 3 plus 1. Now, let's do the little bit of the arithmetic here. 3 times 3 is 9 plus 5 is 14. A times 3 minus 3. Well, 3 minus 3 is 0. Ha! That's what's meant by zeroing out. Because what is a times 0? Nothing. It's 0. And so it's canceled out. It's A is gone because it's effectively 0. Over there, it's 2 times 3 plus 1, which is 7, so I get 7b. And notice the equation here. 14 equals 7b. If you divide both sides by 7, that tells us b is 2. Ta-da! Right? And that's it. So b is 2. And I'm going to write this over here. b is 2. Okay. Whoa. Go back. Now, that was the first 0, and that let us find b. We still need to find a. So I'm going to erase some of this. I'm going to erase that and that. So 3 was the first 0. The other root was negative 1/2. So replace all the x's with negative 1/2. Negative 1/2 here, negative 1/2 here, negative 1/2 here, right? And do the math. 3 times negative 1/2, well, that's negative 1.5, added with 5, equals a times negative 1/2 minus 3. That comes out to negative 3.5. And then 2 times negative 1/2 is negative 1, plus 1 is 0. So the b term is canceled out. And so what I have here is negative 1.5 plus 5, which is 3.5. And then the coefficient on a is negative 3.5. So if I divide both sides by negative 3.5, this yields a is negative 1. Yay, we found it. So a is negative 1 and b is 2. But don't stop there. Finalize what our goal was. Therefore, you don't have to put the 3 dots, but therefore, the partial fraction, or rather, the complex fraction, this guy, that I'm just copying down, this thing equals a over 2x, that's negative 1 over 2x plus 1, plus b, which is 2, over x minus 3. And then you box this, and that is the decomposition. Okay? And that's how you do the zeroing out method. Once you set up the equation, you just plug in the roots of the factors, and that ends up helping you figure out what a, b, all the constants are supposed to be. Now, I want you to be careful with this method because it's really efficient for simple ones like this. Other ones you have to get really creative with, and we're going to see that later down in the video, okay? But that is the premise. Okay. And by the way, grading guidance, I am looking for, or your teacher is looking for, maybe it's not me, maybe you have another teacher, I don't know. I don't know what year it is. I don't know if someone's watching this in year 2030. That's giving me an existential crisis. Okay, I'm going to be 33 by then? That's insane. Oh, wow. Okay. We're not thinking about this right now. Okay. So anyway, grading guidance. Make sure you finalize your answer here. Yeah. Every year I teach this, a lot of students stop right there. I am going to be picky. I'm going to say -2 or -3 or something if you don't finalize and make that nice, pretty answer there. So you make sure you do that, okay? Because that's the goal, right? I don't know, just find A and B. I want to show what the, 2 fractions were supposed to be. Okay. All right. Method 2, systems of equations. Decompose the rational expression. So we're going to do the exact same thing here, but it's a second method, a different method of doing it. I'm going to switch back to red. The setup, though, is the same, as I mentioned. So factor the numerator and denominator, right? Sorry, scratch that. You don't need to factor the numerator. That's not true. That's not true. You can leave that like there. factor the denominator. X plus 1, x minus 1. We know that because x squared minus 1 is a difference of squares. He's classic. Again, I see two linear factors. There's no quadratics here. There's no repetition. It's still the same basic setup that we just were practicing. So x minus 5 over x plus 1 and x minus 1. Now, I'm going to set this equal to an unknown a over x plus 1 plus an unknown b over x minus 1. Then I'll multiply by the LCD, which is x plus 1 times x minus 1, which if you want to try that, these denominators will cancel. You're going to get x minus 5 equal to, the x plus 1s will cancel. You'll get a times x minus 1, and then the x minus 1s will cancel, and you'll get b times x plus 1. And you'll be left with this. Now, if we were doing the zeroing out method, right, we would look for the roots and plug those in. So if you wanted to do it here, you would choose x is 1 and x is negative 1 because 1 would cancel out a and negative 1 would cancel out b. But that's not the point of this example. This example, to see a different technique, and that's using systems of equations. Huh? How does that work? Well, we're going to do something really creative here. Distribute the terms. So I'm going to distribute a, say ax minus a, plus, now distribute the b, bx plus b. Okay, that's done. Next, group your like terms. Now you say, what? Group what like terms? Okay, well, you would say if you had 2x squared plus 7x plus 1 plus 3x minus x squared, what would your like terms be? Well, 2x squared and negative x squared would be 1x squared, and 7x and plus 3x would make 10x, and then 1 doesn't have a like term, so it's just plus 1. That's what we mean. The x's are kind of the indication of what is alike or not. So, in this case, your linear terms are ax and bx, yeah? So I'm going to group those together, and I'm going to use the associative property of parentheses to show that. The parentheses aren't doing anything. They're just a visual way of grouping within that addition, plus the constant here. So what doesn't have an x? The negative a and then the plus b. Those don't have x's. And now I'm going to do something neat. Once you have grouped these, you're going to factor out the variable, not the constant, the variable. And it's always going to be GCF factoring. So x minus 5 is not changed, but ax plus bx, you're going to factor out x. Now, a lot of times we write it this way, right? It's just what we do. We take the x and we pull it out to the side, to the right here, right? To the left here. I'm going to change this a little bit and actually write that product to the right. Remember, 2 times 3 is the same as 3 times 2, so this is fine. Multiplication order doesn't matter for stuff like this. So I'm putting it on the right for a reason. And then there's the constant, right? Well, here's the thing. This polynomial is equal to another polynomial. And maybe you're seeing it, maybe not. Let me help you a little bit if you're not. Say you had 2x squared plus bx plus 7, and that this was equal to 2x squared plus 3x plus 7. The conclusion would be that the letter b is 3. I think you'd agree to that, right? Polynomials, whatever polynomial you have, you really won't have polynomials that are equal to other polynomials unless their coefficients are the same on every degree term. In this case, if you knew 2x squared plus bx plus 7 was equal to this other one, the conclusion would be that the b value simply must be 3. And if maybe now you're seeing it, you're saying, well, the left side, right, this guy right here, is 1x minus 5. That's 1x minus 5. The reason we group this like this is this coefficient on x is 1. And this constant term added at the end is equivalent to the minus 5 at the end. So what this does is create a system of equations. A plus b, the coefficient on x, is 1. Negative a plus b, the constant at the end, is negative 5. And once you have a system of equations, what can you use? Oh my gosh, matrices. Oh, look who's returned. Yes, hello. Oh my goodness. Hello. Oh, the heart is shimmering. It's beating. It's pulsating. Oh my gosh. I'm going to have a heart attack. Yay. Matrices have made their return, finally, at last in our class, right? Unit 3 was not just this thing we learned and left in the past. Matrices and systems have great utility, and this is one of them. So, you can set up a matrix. By the way, obviously you can solve this by hand with a simple elimination, right? I mean, you can literally see, look, add these, the a's cancel, and 2b equals negative 4, therefore b is negative 2. That's great. But the reason I'm pointing out this is this technique's really helpful for when things get complicated. And once you have a matrix, you can use a calculator to solve, okay? So if you want to get, I'm going to show a real quick rundown of those steps again. We want to make our matrix, which is, okay, we're going to come here. Oh, what were we doing last time? Let's get rid of those. Okay, so once you have your graphing calculator, go second matrix. Go to delete that. Second matrix, go to edit. Edit your matrix. We want a 2 by 3 matrix. And the numbers we had were 1, 1, 1, negative 1, 1, negative 5. So 1, 1, 1, negative 1, oops, sorry. Sorry, I'm typing. It's kind of harder on iPad, okay? Negative 1, and I already forgot the number. Okay, 1, and then negative 5. Got it. 1, and then negative 5. Boom. Okay, I'm going to quit out of this second mode, second quit, and then I'm going to go back to the matrix menu, go to the math option, and you're going to scroll down until you find something called RREF. That stands for, if you remember, row reduced echelon form. Click second matrix, and then in this names column, select that matrix A and click enter. This puts it in row reduced echelon form, which tells us what A and B are. So now I'll copy down that matrix. Once I do RREF, I get 1, 0, 0, 1 here, and I believe it was negative 3, or actually it was 3 and negative 2. Is that right? Yes, 3 and negative 2. So I get positive 3 here, negative 2 here. And remember, when we interpret those, this column was for A, this column was for B, so that tells me A is 3 and B is negative 2. Hooray! And so now I celebrate by saying, therefore, the fraction x minus 5 over x plus 1, x minus 1 can be broken up where A is 3 over x plus 1, and then minus 2 over x minus 1 from the A and B values that I found from my matrix. And thus, the work is done. Oh my gosh. Is this not amazing? Look at this. 2 just beautiful methods in algebra of getting this. Yeah. One of them using roots and factorization of things, and the other connecting back to Unit 3 with systems of equations. Oh, it's just so powerful. I love it. It's amazing. And so that is how that is done. Yeah? And that's the 2 methods. Now, when it comes to these methods, it is your choice on which one you want to use. But you might like method 2 if the problem gets really complicated. Yeah? And the next couple examples are going to show you why zeroing out can be just a little tricky sometimes. It's not always going to be so efficient, okay? It's not bad. It's still a great method. It's still my favorite method, but sometimes I might actually prefer method 2, and the next 2 examples are going to do that, okay? So these are the next couple, and these are going to be a little bit different in their setup. So let's decompose this. Start by factoring the denominator. We have a GCF of x, and then I factor that out, like so. And then that's a perfect square trinomial, which means it's x minus 2 squared. Yeah? X squared minus 4x plus 4 is a perfect square trinomial. Factoring is x minus 2 squared. And so the factored expression, what I see here is something interesting. I say the types of factors. Well, what are the types? X is a simple linear factor. That's fine. X is a linear factor. X minus 2 is also a linear factor, but the power of 2 means being squared means it's repeated. This is an example with repeated linear factor. Yeah? And so let's see how you set this one up, because the setup is slightly different. If you come back to the front page here, you'll see that repeated linear factors, you have to account for every multiplicity, right? From 1 up through the highest power. So since I have a power of 2, the decomposition is going to look like this. X squared minus 5x plus 8 over x times x minus 2 squared will be broken up as the following. A over x. The linear term is simply, that hasn't changed. X is a linear term, so it's a over x. Plus x minus 2 to the power of 1, and then a constant on top. Plus the next power of x minus 2, which is squared, with a constant c on top. Yeah? And you have to put this term, because the thing is this is your lowest common denominator. It could be comprised of factors of x, x minus 2, or x minus 2 squareds, because this could be its own individual term separate from this one. Okay? Now, you have to multiply this by the LCD, right? So you need to take this whole thing and multiply by x and x minus 2 squared. Now, when you do this, the left side, I don't know if you're noticing a pattern here, but the denominator always cancels because the left side has the LCD in the bottom. But then on the right side, you know, we'll be careful here. A over x, the x cancels. You still have a times x minus 2 squared. For the b term, one of the x minus 2's canceled. You see, because this is x, x minus 2, x minus 2. So one of those cancel, but you still have x times x minus 2. So it's plus b x, x minus 2. Plus, and then you have this one where the x minus 2 squareds both cancel, and you're just left with x here. So it's cx. And so that's the setup for the decomposition. From here, we're going to explore both of the methods again. So the zeroing out method, how's that work? Well, my little lasso tool, come here you, right? Come here you varmint. There it is. Because we're lassoing it, right? He's a varmint. Okay, anyway. The text is in me. All right. So the zeroing out method. We want to identify the roots. What are the roots of your factors? We have x minus 2, so 2 is a root. And you also have x, where 0 is a root. But you don't have any more than that. Just 2 and just 0. And that's because 2 is what you call a repeated root, right? It's a double root happening twice because it's x minus 2 squared. Okay, So we're going to plug in 0 to start here. And let's just do the algebra. 0 squared minus 5 times 0 plus 8 equals a times 0 minus 2 squared plus b times 0 times x minus 2 plus c times 0. Oh, sorry. X minus 2 is technically, I should write 0 minus 2 here because I plugged 0 in for all the x's. Okay, well, 0 squared is nothing. 5 times 0 is nothing. So I'm getting 8 equals... Here you have 0 minus 2 squared. That's negative 2 squared, which is 4, which is multiplying a. B times 0 is 0, and that 0 times 0 minus 2 is 0. So that's gone. And c times 0 is 0. Therefore, 8 equals 4a implies that a is 2. And so we found a. Now we plug in the other root. X is 2. So 2 squared minus 5 times 2 plus 8 equals a times 2 minus 2 squared plus b times 2 minus 2 plus c times 2. Now, we'll do the arithmetic. 2 squared is 4 minus 5 times 2 is 10 plus 8. That's 12 minus 10, that's 2 equals. Here, 2 minus 2 is 0. 0 squared is 0. A times 0 is gone. This 2 minus 2 is also 0, which cancels all of that. And so all I have left is c times 2, or 2c. Thus, c is 1, if I divide both sides by 2. Okay, and so that found me a and that found me c. But now... And if I was teaching class, I would let you guys be trying all this for yourself without me walking through it. But this is, at this point, students say, well, how do I find b? Because I only had 2 roots here, and they only let me find a and c. So how is b found? Well, this is where you have to get a tad creative. You can plug in the roots because those cancel things, and that makes that kind of nice. But if it doesn't cancel, you still have an avenue. Plug in a different number. I mean, we plugged in roots because that makes 0, but we don't have to make 0. So pick a number. Pick a simple number would be helpful. I'm going to pick x is 1. Yeah? And I'm going to plug 1 into this equation. So it's 1 squared minus 5 times 1 plus 8 equals a times 1 minus 2 squared plus b times 1, 1 minus 2, and c times 1. Let's scroll down and do that arithmetic here. Well, that's 1 minus 5 plus 8, which comes out to 4. And then here, 1 minus 2 is negative 1. Squared is positive 1. So that's 1a. And then this 1 minus 2 is negative 1, which when multiplied with 1 is negative 1. So that's the coefficient on b. It's minus b. And lastly, c times 1 is just c. Well, great, Mr. Spake, but what am I supposed to do with that? And I say, haha, look, we know A and we know C. What that means is I can plug in 2 for A and 1 for C, meaning 3 minus B is 4, subtract 3 from both sides. I get negative B is 1, therefore B is negative 1. Thus, I have found all 3 methods using the zeroing out method. So you have to get a little creative once you run out of zeros or roots, but you can still find it because those help you find unknown constants, which you can plug back in, and it'll be fine. Yeah. So what's the decomposition, right? Let's see. A over x. A was 2 over x. And then plus b over x minus 2. So that's minus 1 over x minus 2. And then c over x minus 2 squared plus 1 over x minus 2 squared. And that is our decomposition. Oh my gosh. That's so great. It's so amazing. I love it. And that's our decomposition. Okay? All right. That's the zeroing out method. Let's do it again. Yeah, let's do it all over again. But we're going to do the systems method now. So I'm going to, again, round you up, you varmint. Come here. And here's my equation again. So how does the systems method differ here? Well, it's actually the same thing we were doing as the first question we did with systems. Expand everything. So the left side's not going to change. But the right side, we're going to do some distribution. We're gonna expand that square there. X minus 2 squared is this. And then I'm going to hold off on that one. And so then the next line, if I write this, I'm going to distribute the a to all of those terms in the trinomial. Ax squared, minus 4ax plus 4a plus, now we're going to distribute the bx term, bx squared minus 2bx plus cx. And now we rearrange our like terms. So I'm going to use some different colors here for you. Ax squared and bx squared. Those are like terms. Let's switch to yellow. Negative 4ax, negative 2bx, and positive cx are like terms. And the last number, 4a, is the constant. Okay? And notice how I group them in descending degree here, right? Then you can factor out the x squared. A plus b x squared, switch back to yellow, plus negative 4a minus 2b plus c x, and then the last term, plus 4a. This corresponds with this guy, 1x squared minus 5x, and then the last term, wrong green, plus 8. So there's my equations, right? The coefficients set up a system of equations. The system is going to have three things. The first coefficient, a plus b, is equal to the coefficient on x squared, 1. The next line, negative 4a minus 2b plus c, this equals that coefficient, negative 5. And then the last one, right, is 4a, which equals 8. And just by the way, this is really a simple system to solve, and a lot of times they are, yeah? Do I actually need to go get the calculator? No. You can solve for a here. Then once you have a, plug it in here and find b. And then once you know a and b, you can find c in the middle equation. But you don't have to do it that way. You might prefer this method because you get to use the calculator for it, in which case, let's set up a matrix, okay? But if you want to solve this by hand, by all means, go solve it by hand. So this column's A, this column's B, this column's coefficients on C. So then that's negative 4, negative 2, 1, negative 5, and then 4, no B, no C, and this equals 8. And so that is the matrix, which again, you could solve by hand. You don't have to do this. And I'm going to make my matrix now. Or should I do Gaussian elimination first for old time's sake? No, we're not gonna do Gaussian elimination. Though I love it. Whoa, 3 by 7, 3 by 4. How about that? Okay, what's the first row? 1, 1, 0, 1. Okay. 1, hello, 1, hello, 0, 1. Okay, the next row. -4, -2, 1, -5. -4, -2, 1, -5. Oh, that was an 8. Get out of here. -5. What? You're kidding. -5. Boom. And then the last row. 4, 0, 0, 8. 4, 0, 0, 8. And now that I have this, quit out. Go back to the matrix. Click Math. Look for row reduced echelon form. Matrix. Oh no, not inverting it. I'm pressing the wrong buttons. Second matrix. Matrix A. Click Enter. I get 2, -1, 1. So, and if you're showing your work on here, I'd like you to show the output matrix to know what your calculator got. And it said, one more time, 2, -1, +1. 2, -1, +1. And since my columns were A, B, C, A is 2, B is -1, and C is 1, which this matches the A, B, and C we found over on there. Hooray again! Oh, so many celebrations. This is fantastic. What a great video this is. I mean, seriously. And you know what? I don't know if any calculus students have stumbled upon this, but if you have, I'm so glad you've joined us in this Algebra 2 journey of breaking down partial fractions, because we're really doing a lot. Yeah, these are some just amazing problems. Oh my gosh. Okay, and so that's that one. But we still got one more to go, okay? I know this is an extremely long video, but I'm hoping you're enjoying it, and I'm hoping it's helping you out a little bit. Last one, number 2. Decompose this rational expression. Okay. So we got to factor again, right? We love factoring. You say, Mr. Spake, are you getting tired? And I said, no, of course not, student. And I'm going to take out grouping. I'm going to do grouping method with GCF. Take out x squared, and I get x plus 2, plus GCF 4, and I get x plus 2, leaving me x plus 2 and x squared plus 4. So that's the fraction. X squared plus 7x minus 6 over x plus 2 and x squared plus 4. Now, this is yet again a different example. And so you have x plus 2, which again is a linear factor, but x squared plus 4, that's not linear. X squared is quadratic, but x squared plus 4 can't be factored further, so this is an example of the irreducible quadratic case. All right, so it's set up again quite differently. So I'm going to lasso this. Come here. I'm going to do that. All right, there he is. Let's make you a little bit bigger. Oh, I love vectors. I love that vector technology there. Okay, and this equals, well, let's go back all the way. So we know how to deal with linear terms, but irreducible quadratics, because it's been a minute, right? Irreducible quadratics. If you have a quadratic here, the term on top is an unknown linear polynomial. So we're going to use ax plus b in the numerator, okay? Oh, I don't know why I'm doing that. Let's go back. So a over x plus 2, that's the same old, same old. What's new here is the x squared plus 4 on bottom. You need a linear polynomial on top. Linear would be bx plus c, yeah? And by the way, again, the letter choice doesn't matter because you could have set this up as ax plus b over x squared plus 4 plus c over x plus 2. And that would be the exact same thing, okay? But the idea is the unknowns in the top of that irreducible quadratic is a linear term, bx plus c. okay? We're going to take this and multiply by the LCD, x plus 2 and x squared plus 4. I don't want to explain this a bunch because we've been doing this a lot, but the left side will stay as is. And the right side, the x plus 2's cancel, getting you a times x squared plus 4. Then the numerator is a grouped linear term, bx plus c. So you have to put those in parentheses. And then the factor that's next to it is x plus 2. Okay? And so we're going to do, again, both methods, zeroing out and systems. Which, remember, once you kind of do enough practice with this, it is up to you which one you'd like to use, okay? On quiz and test, it is totally your choice which method you like. I am, for the purpose of this video, modeling both so you get to see how both work, okay? All right, zeroing out. What are our roots? Well, negative 2 is a root because of x plus 2. But what's the root of x squared plus 4? 2i and negative 2i. I don't know if I want to do that. I don't know if I want to plug in imaginary numbers. I'm not sure how that's going to work out. Could I do it? Well, why don't you try? Maybe you could try it and get back to me and see what you think. Or maybe I'll do it at the end of the video. Yeah, maybe I'll do that. Okay, so let's plug in negative 2 to start with here. So negative 2 squared plus 7 times negative 2 minus 6. And then negative 2 squared is 4. So I'm just going to go ahead and do that. Plus b times negative 2 plus c. And then negative 2 plus 2. Okay, so watch what happens, right? Negative 2 squared is 4 plus, or more like minus 14 minus 6. Am I doing that right? Negative 2 squared. It is negative 2, right? X plus 2. Yeah. Okay. Sorry, I was just making sure. 4 minus 14 is negative 10. Minus 6 is negative 16. And then on the right side over here, you get a times 4 plus 4. Well, 4 plus 4 is 8a. Right here, we get lucky here. Negative 2 plus 2, 0. 0 times bx plus c, this is gone. That's zeroed out. Therefore, we can find a. It's negative 2 by dividing both sides by 8. And thus, we're very happy with that. Yeah? But now, what do you do to get rid of a? You see the x squared plus 4 here. Well, there's no more zeros to use unless you use imaginary numbers, which we're not really going to do right now. But I could, perhaps, you see this bx term? That term itself could be made to go to 0 if you used x is 0. So watch what happens. 0 squared plus 7 times 0. I'm looking at this. 0 squared plus 7x times 0 that's negative 6, which equals 0 squared plus 4. That's just 4a plus, and now I'm getting b times 0 plus c times 0 plus 2. Okay? Clean this up a little bit. 4a. Well, we know a. A is negative 2. So 4 times negative 2 is negative 8. B times 0 is nothing, and that's just 2, so that's just plus 2c. Add the 8 over, and we get 2 equals 2c, leading us to find that c is 1. And now that you've found a and now that you've found c, you can plug in any number you want. I think a good number here would be 1, I think. Do I like 1? Yeah, I like 1. I like it. It's good. So I'm going to plug in 1. x is 1. So 1 squared, again, I'm just looking at the top here. I don't want to zoom in back and forth. 1 squared is 1 plus 7, that's 8, minus 6 is 2. And then 1 squared plus 4 is 5, so that's 5a. B times 1 plus c, where c is 1, that means it's plus b plus 1. I don't know if I lost you there. I hope not. This bx plus c, b times 1, because we're plugging in 1, but also c is 1, so it's plus 1. Okay, so the term is b plus 1. Multiplied by x plus 2, but we're plugging in 1 for x, so 1 plus 2 is this times 3. And remember, a was negative 2, right? He was a negative 2. So 2 is negative 10 plus 3b plus 3 through distribution. Add the 10, you get 12. Minus the 3, it becomes a 9. 9 equals 3b. Divide both sides by 3, and b is 3. Yes. Okay, so we found it. It's good. It works, right? A is negative 2, so the decomposition, right? Negative 2 over x plus 2, plus b is 3, c is 1. So it's 3x plus 1 over x squared plus 4. That's the decomposition. Whew. Lengthy process there, huh? Yeah. So the more and more complicated these get, the less and less zeroing out is super quick and efficient, because, you know, negative 2 was fine. That was easy, quick, and clean. But you had to do a little bit of thinking to find the 0 to get rid of b. And then you had to pick another number and do some substitution to find that. Yeah. And so that is done there. Let's see the systems of equations method. Let's see Paul Allen's card. Okay, let's see the systems. So I'm going to copy you one more time. All right. Okay, distribute this guy, right? Because that's the premise. Do distribution. I'm going to switch to blue here because the red is giving me a headache. Ax squared plus 4a. And then bx times x, that's bx squared, plus b times 2, that's 2bx, plus cx, plus 2c. Come here, you, 2c. Okay. All right, let's rearrange our like terms, right? So the x squareds are going to go together. Ax squared plus bx squared. No more x squareds. And if I factor that out, it's a plus b times x squared. And then I have 2bx plus cx. And that's it. So that's 2b and c factored out from the x. And then 4a plus 2c at the end. Plus 4a plus 2c. That's plus 4a plus 2c. Line this up with the other polynomial. 1x squared plus 7x minus 6. Setting up our system, we get a plus b is 1. 2b plus c is 7. And 4a plus 2c is negative 6. Which, remember guys, you can do substitution and elimination techniques by hand if you would like, or set up a matrix. So we're going to use the calculator. 1, 1, 0, 1. Again, ABC here. You don't need to write the ABC. I'll know what you're doing, but just, for you, the viewer. 0, 2, 1, 7. 4, 0, 2, negative 6. Okay, let's go put them in the calculator. 1, 1, 0, 1. Yeah? All right, I'm going to be quick with it. 1, 1, 0, 1. Here we go. Oh, that's already there. Okay, that's coincidental. 0, 2, 1, 7. Okay, 0, 2, 1, 7. And then 4, 0, 2, negative 6. 4, 0, 2, negative 6. We're going to do RREF of A again. And I get negative 2, 3, and 1. Negative 2, 3, and 1. And that's that matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. So conclusion. A was 2, negative 2. B was 3, and C was 1. Which is exactly what we found here. A was negative 2, B was 3, and C was 1. Getting you the exact same partial fraction decomposition. Take a nice sigh, everybody. Just take a nice sigh of relief. We did it. That was just amazing. How much math? Look at all this. Look at all that. It's amazing what we just did together. Yeah. So that will do for this video on what techniques you need to do and know. Really, okay, if you watched all the way to the end of the video, I'm going to go easy on you on the test, okay? I'm not going to give you some crazy, insane thing. It's just going to be if you get the basic idea. But I wanted you to see this, practice this, be exposed to it before you ever take this class called Calc 2 or BC Calc, because this can be a lot to learn when you're already learning a bunch of calculus anyway. And so it's kind of nice to have this background and see this. And it's also fun. It connects a lot of the algebra we've done before together. So it brings purpose and meaning back to matrices. And I don't think we're totally done with them yet either. They still might pop up in the future as well. Okay? All right. I did have one more thing. Should we look and see what happens if you plug in a complex number? Let me erase all this. Yeah? Just for fun. You can click off the video now. Bye-bye. Bye-bye. This is like when you wait to the end of the Marvel credits, right? And then you're trying to see what the end credit scene is. This is the end credit scene that, all the fans wait for. What happens if you plug in 2i? This will be interesting. 2i squared plus 7 times 2i minus 6. I don't know if I've ever done this before or not. 2i is the root of x squared plus 4, so this will cancel out and be 0. Then it's b times 2i, so that's 2bi plus c multiplying with 2i plus 2. Yeah, I don't know about that. You know what I mean? 2i, because that cancels out a. But we found a, right? To start with, we got negative 2. But then, hold on, everyone. Let me play around. 2i squared, that's 4i squared, that's negative 4. That's a real number. Plus 14i minus 6 equals 2bi. Okay, but times 2i. Whew, look at all this, okay? Oh, wow. 2 times 2 is 4. I squared. That makes negative 4b. Plus 4bi plus 2ci plus 2. I think I know where I'm going with this. Negative 10 plus 14i. That I'm combining the negative 4 and negative 6 there. And then, I think this works. Then the constant term is negative 4b plus 2. And I'm switching to systems of equations. So I'm doing the zeroing out method, but I just switched to systems. And now what this means is negative 4b plus 2 is negative 10. That means you can solve for that. And then 4b plus c is 14. But, you know, so let me solve for b here. Negative 4b is negative 12, meaning b is 3. Haha, that's true. We knew that. And then 4b plus c is 14. But now we know b, so that's 12 plus c is 14, means c is 2. Bada bing, bada boom. Oh, that's what we say. I say bada bing, a bada boom. We say epic sauce, yeah? That's what we say. We say that is amazing, that is fantastic. Also, I don't know if you know what I did just there, but I did the systems of equations method, but instead of looking at it as a polynomial, I looked at it and arranged it as a complex number. So I wrote it as a plus bi, and I related the real components like this, and the imaginary components like this, and used the exact same coefficient technique. So, as I said, bada bing, bada boom, you can take the zeroing out method and then switch to systems, and it'll also work. Did that make it an easier method? No, but it was pretty epic. Okay, that's your Marvel end credit scene, so go away. Stop watching this video, okay? You've watched enough. Thank you for giving me your attention, and I hope this helps you out. Love you all, and see you in the next one.